Good morning, everybody. Once again, my apologies for yesterday's lab. We're still sorting out. We are unpacking our boxes as we do labs. So it was the first time that lab had been unboxed, and it had broken. Moving on, right? We've got today, Thursday, and both days next week to cover 3 sections of a chapter. What does that tell you? Okay? It means it's important. Okay? And important in physics means it's fun, and fun in physics means it's hard. Okay? There is a deep, deep level of understanding that's going to be required of you when it comes to Faraday's law of electromagnetic induction. We're going to roll this out fairly slowly, kind of a turtle's pace, so that we can make sure everything is sinking in. But before we get there, I do want to point out that this textbook kind of lumps together Faraday's law of electromagnetic induction with like the beginning of AC circuits. And that's natural to do. I can understand why the author would want to do it that way. But I am choosing to draw the line between those two things. And so the sections 1, 2, and 3 for this chapter will be on this exam. We will get to the other sections in chapter 30 in the next unit.
Is our test before or after spring break?
It's after spring break. Wait, that's a good thing? It's neither good nor bad, but okay, right? So just be aware, right? You're going to see 2 chapter 30 homework assignments. I think it says chapter 30 part 1 and chapter 30 part 2, right? That's what's going on there, right? We're not doing all of chapter 30 before the exam. We're only doing chapter 30 part 1 before the exam. Part 2 will be on the last unit's worth of material. Okay, so what I want to do, okay, we need to talk about a lot of things. Okay, first of all, what I'm about to teach you comes from the absolutely brilliant mind, conceptual mind of Michael Faraday. We've talked about him before, we're going to talk about him again, and we're definitely going to talk about him right now. Seeing that what we're about to study is named after him, right? It's Faraday's law of electromagnetic induction. It's probably a bit of like an overstatement to say that this never would have been discovered. Pretty sure this concept and idea would have been discovered and interpreted and explained, but Faraday did it first. It was probably a good 20 to 50 years away before Faraday stepped in and started explaining what was going on. Faraday was not a good mathematician. He had no formal schooling in mathematics. And yet he rose to be the preeminent scientist of his age, the sort of the Einstein of the time in the early 1800s. And our world, our society, the way that we go about using technology today can all be traced back to a singular moment in the lab of Michael Faraday. And I would like to repeat the experiment that Michael Faraday did that would alter the future of human society and bring us into our information age. Now, this story begins here, and it's not going to end until we get to the very last chapter of this unit. So you're going to have to hold on for the punchline, right? But I do want you to show you the experiment that rocked Michael Faraday's world and opened up modern society as we know it. What's this? That's a solenoid, right? Okay. It's a loop of wires. Matter of fact, it's lots of loops of wire. How heavy is that?
Not bad.
Not bad? It's heavy. I got physics muscles. Rose is stronger than I am, right? But this has got about 5,000 turns in it. Okay, so lots of wire in here, okay? And it's got 2 connectors on it that will let me connect it to a, this is the closest I can get to what Michael Faraday had, okay? It's called a galvanometer. It's a needle on a display, and that needle is connected directly to some plugs, okay? The galvanometer was invented by a guy with the last name of Galva, I think. And basically, it was a rudimentary voltmeter. The amount of deflection, okay, in the needle gave you an indication of the amount of voltage that you had, right? A bigger deflection had a bigger movement of the needle. So what I'm going to do is I'm going to turn on the Elmo so that you guys can see the screen of the galvanometer, right? And then I'm going to connect. It's going to be very difficult for you to see what I'm actually doing up here because this room was not designed for science lectures in mind and doing demonstrations and all that kind of stuff, okay? But I have my coil hooked up to my galvanometer, and it's displaying what right now? Zero, right? There's nothing going on. So my solenoid is connected to my meter. It's just a nice serial connection, series connection, so nothing going on. These are permanent magnets. Is there any non-aluminum metal in this room? Nope. There we go. My cart's made of steel, okay? So these are neodymium magnets, okay? So nice strong magnets, okay? I'm going to take these magnets and I'm going to pass them through the coil. And I want you to see what happens. You ready? What just happened? History just changed. Why? We made a voltage from doing what? Moving a magnet. Can you name a device today that generates electricity from motion? It's called a generator. Before Michael Faraday, everything was gas and burning coal. Steam engines. In this moment, in Michael Faraday's lab, around 1812, 1813, what has Michael Faraday unlocked? The knowledge, the building block, the very basic physics that would form electrical generations that we still use today. But it goes further because Michael Faraday was able to reverse this idea. Can you take electricity and cause motion? What's that called? That's called an electric motor. And before this moment in history, motors were steam engines. But now they could be powered by electricity. We could cause motion by controlling electrons. This is the beginning of us harnessing the power of electrons. And it's going to rewrite the future for our society. I mean, think about all the different ways we tell electrons what to do today. And I'm chemists, I'm not talking about chemistry, right? Because you guys are playing around with your electrons all the time and chemical bonds and stuff. Not talking about that. It's a whole separate branch. I'm talking about altering our physical universe, how the earth works, how society works. Where do you find motors? Electrical motors? Everywhere. They are everywhere in this building. They're in your phones. They're everywhere. Where do you find electrical generators? Not everywhere. Okay? They're mostly centralized in power plants that produce, right? But the idea, right, is that without like the grid and energy voltage production and all of that stuff. How do you harness this army of electrons to do your bidding? It starts with the movement of a needle. And it turns into everything that we use today, from the lights to moving cars to making toast, running your microwave oven. The list goes on, and we're going to explore a lot of these things. But there are things that you need to notice about what just happened. And it's going to be difficult, so I'm going to have to kind of narrate because you can't really see what I'm doing to the solenoid here. So my magnet is very far away from this solenoid, right? And what I'm going to do is I'm going to put the magnet inside the solenoid and set it down. I'm going to set it down right in the middle of the solenoid, okay? I want you to watch what happens to the needle as I place the magnet in the solenoid. Here we go. Moving in and placing. What happened? The needle moved as long as what was happening? The magnet was moving, right? The magnet is inside the coil right now, isn't it? Okay, so let's talk about something you already know, a conceptual framework that we can use to quantify how much magnetic field is inside this solenoid. It's called flux. Remember flux? Electric flux, Gauss's law. What would magnetic flux be? Yeah, it was kind of like an EA. So like we defined electric flux as the dot product, right? But I was so smooth in my transition. It was beautiful. I just forgot to push the button. Thank you. I decided to plug in over here for video audio. I'm going to see if that works a little bit better. But now it just means more walking for me. Okay, now can you see? Excellent. So we defined this as E dot A, right? And we had some, in truth, right, it's this, if we really wanted to get down to it, right? So what would magnetic flux be? Yeah, right? So the magnetic flux, again, symbol capital phi sub b, would be the integral, right, of BdA, right? So what does that mean for my solenoid over here? So we can do several areas here. So the way I've written the flux up there is with that circle on my integral, which tells me something about the area. What's true about the area if I have that circle there? It means it's closed, right? It's a surface area that connects to itself, right? And we know what the magnetic flux is going to be through a closed surface. What's it going to be? 0, right? That's Gauss's law for magnetism. So really, we want to take like a little subset of the flux. We want to do B dot A, where our area doesn't necessarily have to be a closed area. Instead, we're going to define area, like if we want to know the flux through the solenoid, it would be the cross-sectional area of the solenoid. Now this solenoid is a cylinder, so what area are we going to use? Pi r squared, right? Okay, so we know the area of this solenoid. Area does have a direction. In this case, the cross-sectional area of this solenoid would have a direction either pointing out or in. We can just pick out that way as our area direction. And we want to talk about the flux that would exist, right, if I take a magnet and I put it into my solenoid. So with the magnet far away, how much flux is going through my solenoid? 0. There's no flux there, right? Okay. But as I put the magnet inside the solenoid, more and more field lines are coming into the region of the solenoid. And now, is there magnetic, well, now there isn't. Is there magnetic flux if I have my magnet inside? Yeah, right? Because I've got a really strong magnetic field. Now, of course, I'm ignoring the magnetic field of the Earth right now. Okay? But right now, I've got a really strong magnet inside my coil right here. Okay? And so there's a north pole, the south pole, right? But if I just take a slice of this solenoid, I just look at the area inside of that solenoid, are there magnetic field lines passing through that slice? Yes, there is. Okay? It's not a closed surface. It's like a fence in a river, right? We don't have a closed box where it goes in and out. We just have it flowing through.
And that's regardless of you moving the magnet.
Correct. I'm just talking about whether or not there's magnetic flux located inside of my solenoid. Where do my connectors go? Right there. Okay, so connect this back up. Get you to the point where you can see it. Ta-da. Okay, so with no flux through the coil, the voltmeter reads 0, right? Primitive voltmeter. I come over, I put the magnet inside, and the voltmeter goes, right? But there's now a lot more flux in the coil with the magnet inside right now. But it still reads 0. What has to be true in order for the galvanometer to not read 0? The magnet has to be moving. Let's use more scientific terms, especially in the context of what I just taught you about flux. What must the flux be doing? Changing. Delta. Is the flux changing right now? How do you know? It says 0. Okay? But more importantly, the flux is constant. Nothing is being altered here. But if I reach in here and I grab this magnet and I pull it out, do I change the flux in the solenoid? Yeah, it went from a big number to what now? What's the flux in the solenoid right now? 0. I went from some value to 0, right? And that caused the needle to flick. Again, if I change the magnetic flux, the needle deflects. But now that I've stopped changing the magnetic flux, the needle doesn't move. So there's something, it's not just magnetic field. There has to be a change in something. And what does the change have to be? In the magnetic flux. So how do we change magnetic flux? This can be calculated up here, right? Any of these dot products as magnitude of first vector times magnitude of second vector times the cosine of the angle between the vectors. If I have my solenoid, right, like this, and I'm running a magnet inside, then the area of my solenoid and my magnetic field are the same direction. Cosine of 0 is 1. It would just be B times A, right? And I can now look at this and go, okay, how do I change the flux? How do I get this? Now, strict mathematical interpretation of a delta is what? Change. But specifically, it's final minus initial, right? So we would take a final magnetic flux, subtract off the initial magnetic flux, right? And we would get this delta. I'm asking a more broad conceptual question. If flux consists of two vector magnitudes and a direction, how many different ways are there to change the flux?
Could it be like the speed or which, like the force you provided to move the magnet through the solenoid?
Okay, so the rate at which I move maybe the magnet through the solenoid. Like you said force or something, we're going to force, don't worry. That might be Thursday, okay? But let's see what happens here. So I'm going to do both of these with the removing of the magnet from the solenoid. The magnet's in the solenoid right now, okay? So choose your own adventure. Do you want fast first or slow first? There's a 50-50 chance. Okay. We're going to go fast first. Okay? You ready? Watch the deflection on the needle if I go fast. It's kind of hard to see, but where did it max out? At max. Right? Like it went really to max. Okay? Now I'm going to go slowly. You ready? I didn't keep my speed very consistent there. Let's try it again. So it didn't change as much, right? Compared to if I go faster, see how it just really hits and kind of goes quick? Gets that maximum. If I go really, I gotta go really slow. You know what? I need less magnetic field. I can fix this. Let's see if 3 of these magnets. So I was just going in slow. See how it doesn't deflect very much if I go in slow? But now if I go fast, see how it hit? Okay? So I'll put it back inside. So now I'm going to pull it out slow. It's barely deflecting. Okay? Coming out slow, trying to keep it as steady as I can. So I get just a little tiny bit of wiggle, right? But now if I go pull it out fast, it pegs. So there is something to the rate here, right? I'm generating more voltage the faster I make this change. But we still haven't answered the question of how many different ways are there to change the magnetic flux? Look at BA cosine theta. How many things can change? 3. B, what's B? Magnitude of magnetic field. So the strength of the magnetic field, right? A, the area of the coil. And theta. The angle at which flux is the dot product between 2 vectors, an area vector and a magnetic field vector. Theta represents what? The angle between them. So how do I change the angle between them? Rotate something. Either the area or the magnetic field direction, or both. I can't do both. I'm going to do one.
Seems like it's easier to rotate the magnet than the...
Well, yeah, I'm not going to rotate the solenoid. The thing's heavy, okay? But what I'm going to do is I'm going to go down inside of the solenoid, and I'm just going to turn the magnet in my fingers like this, okay? I'm just going to spin it. So here it is down inside of the solenoid, holding it as steady as I can, and now I rotate it. And what happens as I rotate it? It's going to oscillate, which makes sense because I'm going from like 0 to 180 back to 0, right? As I go through, so it goes back and forth. What kind of circuit do we call this if we have voltage going back and forth?
Alternating current.
That's coming after the test, okay, right? But I can rotate the magnet inside of the coil. Remember, I can rotate it outside the coil. I just need a change in flux, right? So we come back to, I'm getting the hang of it. Come back to this, right? We can, where did I put my pencil? Right here. I'm going to have to tie this to me somehow. I don't know what's going on. We can change the magnetic field. We can change the area. Or we can change the angle. Or we can do multiple of those at the same time. Doesn't matter. But the point is, all of those things can be used to change the flux. Changing magnetic field strength is just me being either closer or further away from the coil, right? The magnetic field of this magnet is going to fall off as 1 over r squared, right? So, or 1 over r. So I can change the strength of the magnet depending on how close or how far inside or anything like that, because the field strength is going to be bigger the closer I am to the magnet. How do I change the area? I've got to change the shape of it. Can I Hulk out here and turn green and pull this and turn it into a square? The answer is no, I can't do that, okay? Even though I have been exposed to gamma radiation a lot in my career, right? Which is true, and may explain a lot. But if I suddenly change the area of this circle to a square, does that change the area? Yes. If I take a square piece of wire and I attach 2 wires and I pull those 2 wires suddenly and it flattens out, does that change in area? Yes. None of those are practical, right? You would not engineer a motor where the coils in it are changing the shape all the time. It would cause metal fatigue and it would fall apart right away, right? Okay. So even though we can change the area, typically we don't. Because the change in area is literally a change in the magnitude of the area. There will be one example where we will change the area of the loop and it's connected to something that you don't, is going to come out of left field. Okay? But is very much in the zeitgeist. Okay. Change the magnetic field, that's easy, right? Bring the magnet right further away, that's the strength of the magnetic field, right? Change the area, in terms of engineering, not easy at all. Theoretically possible, but the engineering of that is difficult. And then changing theta. Again, that's a rotation of what? How the magnetic field and the area vector are lining up. So if I put my magnet inside of this solenoid and I just rotate like this, does that change the orientation of the area with respect to the magnetic field? Not if the magnetic field is along the axis, right? That will cause no change. I would have to rotate this thing like this, right? And that's essentially what I was doing with the magnet. I was rotating it perpendicular to the area of the coil to get those changes. So it turns out that rotating the coil, or actually rotating the magnetic field, is one of the most engineering-friendly ways to create the motion that we need. Or vice versa, create the electricity that we need. But it's important that you understand, it's not just magnetic flux that matters. What does that flux have to do? It must change. It has to change. If it doesn't change, nothing is happening. So how did Faraday sort of put together all of this into an idea? Well, the idea was, and you're going to see this written a lot of different ways. I'm going to write it like this, okay? The EMF, the magnitude of the EMF, is going to depend on the number of turns in your loop. You got to have a loop of wire. You don't have a loop of wire, you're not going anywhere, okay? It's got to be a solenoid or a loop. If it was this solenoid, I would put n equals 4,000 and just go, right? But key to this is this change. I can write this a lot of different ways. I'm a little bit conflicted about how I should do it. I will use this one, because you guys know calculus. Again, those little d's are really what? changes. They're deltas. It's just that your size of your change is how big? Infinitely small. Okay. But notice, now we're back to this idea about we need a rate. A rate is always a change per time interval, right? So the d phi that's up there, right? Our d phi is the d of the BA cosine theta in general, right? And again, that d can apply to the magnetic field, it can apply to the area, or it can apply to the angle. But what's important is that that magnetic flux be changing in time. If it's not changing in time, you are not getting any of this. And what does that symbol mean? It's EMF, electromotive force, but it has units of volts. This is a voltage, right? We use the symbol E to indicate it's like the perfect voltage without any resistance in the system, right? So our voltage is going to be equal to the change in magnetic flux per time times the number of loops we have in our coil. And this statement right here, that is Faraday's law of electromagnetic induction. Okay, let's pull that apart. Faraday is Michael Faraday. As far as I'm concerned, the person that invented the modern world. Number 2, law. Scientists, and particularly physicists, do not use that word lightly. What is a law as opposed to, say, a theory or a hypothesis?
Typically, it's true everywhere. The theory still needs to be proved.
Actually, a theory does not need to be proved anymore. Yeah, no, there's a... So my favorite discussion about this whole thing is that 2 decades ago in Texas has been weird for a long time. Just get that out there. A school board required that all biology textbooks have a sticker put on them that said that evolution is a theory, right on the cover of the textbook. Okay? And a bunch of scientists went, thank you. Because theory means that it has passed all the tests. That there is no current evidence contrary to the concepts, ideas, and mathematics that are laid out in what we have attached the word theory to. Now, of course, the school board wanted to do what? Like undermine, right? Okay, undermine this concept of evolution. And if they wanted to do that, they should have said, well, evolution is a guess, right? Or a hypothesis. They should have used that terminology. Scientists don't do a good job of communicating, okay? It's sort of built into our personalities, isn't it? We went into science so that we didn't have to communicate with other people, right? Except through math or papers or something like that, right? We don't get into politics. We don't do any of that. And it's biting us in the rear. We really should be more involved in politics. But politics makes me feel slimy, so I'm not going to do it. Theory has passed every test that we currently know how to implement for the idea. Okay? It has gone from beyond experiment and hypothesis as like we think it happens this way and now we go test it, and then we go test it and we wait for people to come with counter arguments and say, no, well, maybe it's this, maybe, and eventually we get to a theory of how some things work, be it gravity, be it electricity, be it evolution, whatever it is. If a scientist is calling it a theory, then that scientist is saying what? It's definite. Like, unless we get new information about it, right? We've tested it. A law, so a lot of people think of a law as like a graduated theory, right? And I kind of heard that in some of the definitions you were saying. In physics, that's not what a law is at all. A law is a statement about a fundamental relationship in nature. Think of Newton's second law. You don't guess that. You don't theorize that. And you definitely don't derive it. What is Newton's second law? F equals ma. It's only the law that governs how everything works in the universe as far as forces are concerned, right? Okay. So what does it say? It says a lot of things, but critically, it's the relationship between force, acceleration, and mass. And when you're like, well, that's stupid. Of course it is. That's what it says, Mr. Balogh. And that's the point. I cannot derive this relationship. There is no set of fundamental principles that I can put together to get this. This is the fundamental relationship. Now, have we tested this against experiment? Absolutely. You test laws all the time. But a law is a statement of fundamental relationship between things, right? Whereas a theory is kind of a step back from that, where we're saying we think this is how, say, electricity works, right? We have this theory of direct current electricity. Now, in that theory, I've already told you a bunch of lies, haven't I? What's like the chief lie that we talk about in electricity? I've just, nobody's questioning anything anymore. You're all part of my cult, right? And the fact that positive charge goes places? Is that fundamentally what's going on? No. But in our theory of electricity, it's really handy to think of it that way so that we don't get into the weeds about what the electrons are doing. Okay? So electrical theory, right, dictates things that aren't true, but are good conceptual hooks with which to define things that are happening so we can all communicate with each other. So when I say that this is Faraday's law, what am I trying to say? It's fundamental to how the universe is put together, right? Again, I don't derive this, right? I don't derive Faraday's law of electromagnetic induction. What we know is that if you go and change the magnetic flux through a coil, it will be proportional to the amount of voltage that you are going to get out. Our universe is put together this way. Now, of course, Michael Faraday wasn't working in a vacuum. He didn't like all of a sudden just sit there one day with a coil and a magnet and go, ah, right? There were other scientists that noticed things like what we've already talked about. If you run a current in a wire, it causes the compass needles to deflect, right? And what got Michael Faraday going, right, is that he saw what nobody else saw. A current in a wire could cause a compass needle to rotate. Obviously, the compass needle was experiencing a force. What Michael Faraday wanted to know was how that worked and if he could get the rotation to be continuous. And that's when he started thinking about flux and discovering all these kinds of things. Michael Faraday had this ability to see magnetic fields. All of these pictures I've been showing you of electromagnetic fields come straight out of the brain of Michael Faraday. This incredible visualization power. He couldn't do math, hardly at all. But he could do physics with the best of them because he could visualize what was going on. It gives people like me a lot of hope because I don't like doing math either, right? Luckily, there are other people called theorists that do like doing math. All right, so Faraday's law, and that was me being a little bit on a soapbox, but I think it's an important thing as part of your general education to realize, right? You're going into STEM fields. We don't throw the word law around very lightly in physics. You engineers might corrupt it a little bit, but physics. Don't even talk to me about what chemists do. Boyle's law. Anyway, so what do we got? Faraday's law of electromagnetic. What's involved? Electromagnetic. What does electro mean? Electricity. Magnetic. Magnetic field. Back up. Electro isn't just electricity, it's electric field. You don't have electricity without electric fields telling those charges what to do, going down the wires and doing voltages and all that kind of stuff, right? So this is both, isn't it? It's not just the magnetism, it's the electricity and how those electric fields respond to the magnetic fields and vice versa. Faraday's law of electromagnetic induction. What does it mean to induce something? To cause it to happen. When a pregnant person is induced in their labor, right? They apply methods and drugs to get the labor going, right? So that the baby can be delivered. If I'm going to induce learning in you guys, I need to provide an environment, right, that causes learning to happen, right? So that word induction refers to causing it to happen. So Faraday's law of electromagnetic induction is what? Causing electricity and magnetism to happen. Yin yang, vice versa, all that kind of stuff. I wrote it with these absolute value signs around it. You will see in many a place, it's not incorrect, it might even be more correct. It depends on your point of view. But you'll see in a lot of places, you'll see EMF equals negative N, change in magnetic flux over change in time. Okay? And this is where I'll get called, Mr. Barry, you put a negative sign on your, okay, I put absolute values on mine, right? Okay? Because this minus sign is a reminder for something called Lenz's law. Oh, there it is again, right? That we are going to talk about next time. We've got to push it off. I've got other things I've got to talk about first, okay? But again, this minus sign is a reminder of something called Lenz's law, which you are going to hate. Promise you, okay? It's really cool, but it involves several right-hand rules in a row. I choose to write it with the absolute value signs as a reminder for Lenz's law, right? Because Lenz's law will set the direction. Faraday's law will give us the magnitude of the induced electricity, the induced electromagnetism. All right, that's a little bit of a preview though, because we need to talk about, I've got time. Heck, I don't even know if I have time. I'm going to make time. Come on. Here we go. Okay. Let's do... where is it? Here it is. You did not do the right audio channel. Here we go. Let's try that again. Name that tune. Nope. Name that tune. Jack London, Star Spangled Banner, right? Name the instrument. That's an electric guitar. It is music. Okay? He's playing at a U2 concert back in the 80s. So, definitely his style, right? Okay. How did you know it was the Star Spangled Banner? What am I doing? You've heard it before, right?
Yeah.
Okay. And your brain latched onto it and said, yeah, that's the Star Spangled Banner. Okay. How did you know it was an electric guitar? Because of the way it sounds? How do electric guitars work? Vibration. Okay. Does anybody here play guitar? Yeah? Acoustic, electric? Both, because why not? They all have 6 strings, right? Okay. So when you're playing an acoustic guitar, do you need an amplifier? Generally not, right? There are ways to hook up acoustic guitars to amplifiers, but you don't generally need it. It's the shape of the guitar that captures the vibration of that string and sort of pushes that sound out into the room, makes it louder. But an electric guitar has no like sound box attached to it. The shape of an electric guitar can be whatever you want it to be, because the shape actually doesn't matter. It's the pickups. So here's a picture of an electric guitar. I promise this is connected. This is not a tangent. Okay? So do you see the little circles? Right here. Those are called pickups. Okay? And there's another set of them back here. They're out of focus. Okay? How many pickups? 6? For how many strings? 6. And then another set up here to make sure we're catching all the vibration. Okay? This is a tension bar that helps to, this seats the strings. This allows a little bit of adjustment, but you do most of the tuning on the other end of the guitar. Okay. What does a pickup do? Musicians are brilliant people. They know how to describe stuff. It picks up the vibration of the string. How? This is a greatly magnified pickup. This is the string that's going across the top of the pickup. Okay? It might help you if I told you 2 very important things about how electric guitars work. Number 1, the strings of an electric guitar are not the same as an acoustical guitar. The strings in an electrical guitar have little embedded magnets in them. More precisely, sections of the string that are magnetized, okay, with north and south poles in the strings. Inside of the pickup is a coil. How does an electric guitar make sound? You set the string in motion, which causes a change in magnetic flux in the vicinity of a coil. The rate of change of flux of this string, in other words, the frequency of its vibration, will be exactly the same frequency in the pickup. You then take the wires of the pickup, you send them to an amplifier, which is connected to a speaker. And what do you get? A direct application of Faraday's law of electromagnetic induction. Faraday was the most metal guy that ever lived. That sound, that distorted sound that Jimi Hendrix sort of like invented, pioneered, that sound is created by a lot of artistry. And what he would do is he would change the tensions of the strings like on the fly. There's something called a whammy bar, do they still call it that? That allows you to adjust sort of the tone of the instrument and how the strings are reacting to each other. That's all very much rooted in artistry. The basic way that you get that electrical device to produce an acoustical waveform is through Faraday's law of electromagnetic induction. If you want to hear Faraday's law of electromagnetic induction, you just have to listen to electric guitars. I'm going to play the next song because it's going to date me. And unfortunately, it's got a bad rep nowadays. It did not have this reputation when it came out. This is the police before stealing the things. You hear that bass guitar? Okay. This is an iconic 80s bass line, right? Okay. That's an electric guitar. It sounded very different than the one we just heard from the Star Spangled Banner, right? But again, that's about as close as I think you can get to what Faraday's law of electromagnetic induction sounds like, right? We're generating electrical signals in these things. Now, it gets even funner because once you have this electrical signal, before or after you run it, before you run it through your amp, you can put in a DSP, a digital signal processor, which can take those waveforms and turn them into anything you want. My brother-in-law is a musician. He plays a, what do they call it? Pedal steel guitar? It's like a guitar that almost looks like a piano almost. But he plays regular guitar and electric guitar. And he has a set of pedals that when he performs, he can like push a pedal with his foot and it changes the sound of his guitar. Well, I thought it'd be really funny one time if I reprogrammed his digital signal processor, because I've worked in digital signal processors before. This is easy, right? Okay. And so I had one pedal do a chicken. I had one pedal do a pig. I had another one do a sheep and another one do a pipe organ. It was hilarious to listen to that practice that afternoon. It was pretty funny. He didn't think it was that funny. Okay, one more. So everything you are about to hear except for the human voices is electronic. Anybody know what this song is yet? It's a live performance, so they're just kind of warming up to it. You might recognize it as soon as they start. No? Too old? Men at work? Burning down the house? Oh, come on. This is classic. Classic stuff. I know you guys probably call it the oldies now. Something like that. It's good. I saw Devo before the world knew what Devo was. They were performing in Santa Cruz. And we were like, who are these weird guys with flower pots on their heads? They were doing that on like live stage. It was really funny. Wasn't that much into Metallica. So like top 40 just angered me. I was definitely into the alternative scene. And like back then, U2, before they went weird, they were really kind of this alternative, like the Joshua Tree albums and things like that were just works of art. And you had Depeche Mode and you had Men at Work and Tears for Fear, a bunch of, it was all good. It was all good. All right. Modern music, brought to you by Faraday's law of electromagnetic induction. Let's do some more. Well, since we're on the topic of music, let's talk microphones. How do microphones work? Now you know the secret. Got a picture of a microphone. What I don't have is a picture of the inside of a microphone. Okay? So I failed you in this regard. I should try to find, if you take the bulby end off, because the bulby end's not the microphone, it just protects the microphone from being spit on. Okay? It's also something called a popper stopper. There's a membrane in there that keeps it from the what do they call it? Those are plexions or something. It's part of how we shape our mouth that causes microphones to go kind of weird if you into them too much. So they'll put a popper stopper or a membrane, a piece of fabric in between your mouth and the microphone to cause that sudden change in pressure to not be as big. So the top roundy part protects the part that's inside that's the important part, the microphony part. It consists of a diaphragm, a flexible membrane that has a magnet attached to it. This is not how all microphones are made. This is just general idea, okay? And below that magnet is a coil, right, inside the microphone body. So when you talk, the membrane will bounce up and down. Whatever sounds you are making, the vibrations from your voice carried through the air will cause that membrane to go boingy, 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 right? And whatever frequencies are being produced will be transmitted to this coil. Why? How? Faraday's law of electromagnetic induction, right? And then you take these things, you send them to an amp, and you send them to a speaker, right? Or you put a DSP in there and you can sound like Darth Vader or a chicken or whatever, right? Okay? So you hearing your voice for the first time, brought to you by Faraday's law of electromagnetic induction. What do I mean by that? How many of you have ever talked into a microphone and are kind of shocked as what it sounds like? That's how you sound to other people. Okay? I don't know about you, but I sound like James Earl Jones in my head. Why does my voice sound different to me than, say, it does to you? I have a lot of vibrations and frequencies happening in my head. Like, not like mentally, right? But like actual vibrations. So I'm generating the sounds here in my larynx, right? And then the shape of the holes in my head and where I put my tongue and my teeth and all these different kinds of things shape those vibrations, and then I send them out, right? I hear an echo of my voice off the walls that my brain goes, nah, that's not it. And instead, the vibrations coming up through like my jawbones, right? And the different reverbs, bounces in the room all come together to make the sound that I think I hear. The hearing isn't coming from the outer ear, it's coming from the inner ear, right? Whereas everybody else doesn't live in my head. It's a good thing. Instead, you just hear the vibrations as they come out of my mouth, right? Which is why when you stand in front of a microphone and you talk, if you're not used to it, you'll be kind of shocking, right? You'll hear this voice. You're like, that's not my voice. Well, it is. It is your voice. In general, you sound squeakier and higher pitched than you do in your own head. So, microphones, brought to you by Faraday's law of electromagnetic induction. Since we are on a trip down memory lane, back when hard drives were hard drives, right? This is a hard drive. It's heavy, okay? So this plate right here is where the data used to be stored. There's a read-write head that goes across the surface right here. There's a motor right here that controls the spinning of the plates. And then there's a motor up here that controls the read-write head going in and out, okay? I believe, I looked it up once and I figured out, I think this hard drive holds 1 megabyte.
Wow. What year was that made?
This is like a 1 megabyte hard drive. This was a big deal. This is back in the days when hard drives were kind of a new idea.
128 gigabytes.
No, right, right, okay. This is holding 128,000 times more information. I did that wrong. 1 megabyte, 100 gigabytes. That's 1,000 times. What's 1,000 times 100? 100,000. So that's storing 128,000 times more information than this thing is. Imagine carrying this around in your pocket. This motor right here came out of a washing machine. These were cast-offs from washing machine makers, and us old computer geeks would take them and throw them together to make hard drives. Okay, this was a production hard drive. I don't remember who made it, but It's a big hard drive. The reason they were throwing these away when I got here, I was like, no, my gosh, these are wonderful museum pieces, right? The reason I wanted to show you is because it's nice and big and I can demonstrate with it, right? So these disks in here, okay, by the way, this is the part of the hard drive you never want to see. If you are looking at your hard drive like this, your data's gone, right? Okay? The only people that should see the insides of hard drives are those of us who make a living out of fixing them, right? In which case your data is probably still gone, but we can get some of it back. All right, so the data gets stored on the disk, but this read-write head is used to both put the data on and take the data off. How do hard drives store information? Okay, not only are there motors in that hard drive, Faraday's law of electromagnetic induction, right? Not only do hard drives require electricity in which to operate, Faraday's law of electromagnetic induction, but the actual way that you store the information is caused to happen by Faraday's law of electromagnetic induction. I keep losing my pens. Here's the platter of the hard drive. Here's the read-write head that skims across the surface of the hard drive, very close. On the hard drive are areas that can be magnetized. They can be forced to have a magnetic field pushed in one direction or another. If there's no magnetization there, generally that's thought of as a 0. And if the orientation has been forced, that is considered to be a 1. And when you have 0s and 1s, what do you have? Digital binary information. Okay. Inside the read-write head, there's 2 coils. I'm only going to draw one. Okay. But there's a read coil and a write coil. As the disk spins underneath the read-write head, different pieces of magnetization are going to pass underneath that read-write head. So it's going to go from no magnetic field to some magnetic field to no magnetic field to some magnetic field, depending on the pattern on the surface of the drive, right? So when the flux changes underneath this coil, there will be an induced current and voltage in that coil, which sends a signal to the microprocessor that says, information. And then to write that information, to store the file, right, you send pulses through the read-write head to cause the magnetizations to line up on the surface of the drive. Either direction, whether you're reading or storing, hard drives are brought to you by Faraday's law of electromagnetic induction. We're moving towards a solid state future. A lot of our devices nowadays don't have hard drives in them, right? They have solid state storage, memory that has no moving parts and is not stored magnetically. I can wave all kinds of magnets near my phone and my computer. It's not going to do anything, right? So the reason being that that kind of storage is quantum mechanics. And so you need physics 4C before we can talk about all of that, okay? But basically that's just keeping track of electrons in little tiny cells called transistors. So Faraday's law of electromagnetic induction brings to you electric motors, electric generators, hard drives, microphones, modern electronic-based music, the GFIs. We talked a little bit about safety. GFIs, those little things that will trip off in your house. You probably got one in your bathroom, a little test and reset button on the electrical plug, on the outlet rather, okay? The way that that device knows that there is a fault in the ground is through Faraday's law of electromagnetic induction. If the ground isn't connected correctly, it will detect transients in that ground connection. Transients are little electrical signals that are going places. Those electrical signals cause changes in magnetic flux through a coil that's in the switch. And if the coil is sensitive enough, it goes, "Wah! There's a problem," and shuts that thing off. The problem usually being that you've somehow connected electricity to your ground. Traffic lights. Oh my gosh, traffic lights. You go outside of Fresno and it's like traffic lights don't work anymore. Have you noticed this? You go to a different town, LA. Go to LA. Don't go to LA. Okay? But go to LA. You go to traffic and they're all dumb lights. You know what I'm talking about? You pull up, it doesn't detect that you were there. You just have to wait for the dumb thing to cycle. You're all staring at me like this is a new thing. Do you guys get out of Fresno at all? Not really. They're trying. Okay? But have you ever been at a light that's just, you know it's on a timer and it's just not doing anything? Most of the lights in Fresno are not this way. They are smart lights. Okay? Smart because they know what? When somebody is there. How do they know? Have you seen the circles that are cut? I need to find a civil engineer. Why do they cut the circle after they lay the asphalt? Anyway, okay? So there's a circle that's cut in the asphalt, and off that circle there's a line that's heading towards the edge of the street. What's in the circle? A coil of wire. Why would they put a coil of wire down there? What are you about to park over the top of the coil of wire? A big lump of metal. And that big lump of metal is going to interfere with the magnetic field through that coil. And the coil is going to say what? And it's going to detect that something's changed. And it's going to say, oh, there's a car there. I'm going to make that sucker wait for a while. No, it's supposed to, right? Brought to you by Faraday's Law of Electromagnetic. Going through the security checkpoints at museums or stadiums or the airport or something. The metal detector. It's a coil. It's not a doorway to another universe. It's a coil, right? Through the ground, okay? That they are running a current through, which generates a magnetic field, which is a constant magnetic flux. If you, like me, can't remember to take your watch off, I take everything else off. I'm going through naked, but I can never remember take off the watch, right? And you walk through, that piece of metal interrupts that magnetic field. The flux changes, security guards come. This is a story from before 9/11. I wish I heard what Amari just said, but I didn't. This is a story before 9/11. My then fiance had come up to visit. She was living in LA. This is my wife now. She was in LA. I was in the Bay Area. And she had come up. We were at San Jose International Airport. And she was going back home. This was about 3 months before our wedding. And she had gathered a bunch of my things, like awards and medals. They had like a table that had all of our achievements on it or something. And so I had given her a stack of my academic decathlon medals. Because I'm a nerd. Okay? And so she had them in her carry-on bag. She is also a flute player. So she had her flute with her in her carry-on bag, right? This is back in the day before 9/11 when everybody could go into the airport. If you all went through security, fine. You could all go to the gate and kiss each other and say goodbye and cry and do whatever you want at the gate, right? Didn't have to do it outside the airport. And so I was like kind of in the front of the line. I was carrying some big bags. And I walked through. She was the one that was going to go on the plane. I walked through, and I'm waiting for the bags to come off the thing. And I turn around, and all 4 feet 11 and 85 pounds of my fiancé is being shoved up against a wall by a cop. My mother, the kindest soul in the universe, is also being shoved up against the wall. And I just looked, and I just shouted, "What the heck is going on?" The alarms were sounding. Police were running in. It was craziness. I finally managed to figure out, they diffused the situation pretty quickly. The metals had been stacked up and they had sort of fallen over and were right next to her flute. And the poor lady running the x-ray machine was in tears. She was crying. And all she kept saying was, it looked exactly like a grenade. It looked exactly like a pipe bomb. It looked exactly like what we see in training. Be careful when you get married. Metal detectors, brought to you by Faraday's law of electromagnetic induction. All right. What time is it? 12:40. So we did all that. Okay. So let's just do an example so that you can see that there is math associated. There's a lot of ideas, a lot of concepts, a lot of application. That was, by the way, that was a taste of what's coming up, right? Not the stupid old men stories, but like all of the applications, okay? All of these applications. This is how big this is. Like, I think this is bigger than Newton's second law. Newton's second law, build rockets, go to the moon, okay? We're talking about changing the fundamental nature about how our society works. We're talking about steampunk doesn't happen because we don't need steam power anymore, right? We got electrical power. Okay, so why are we talking about lightning strikes? Well, what's a lightning bolt? Treat the lightning strike as a straight wire, because that's what a lightning bolt is. It's a big piece of the atmosphere that's turned into a conductor. So much electric field, so much voltage is built up between the cloud and the ground that it has no choice, it makes a big spark. So we have a big wire. There's our lightning bolt, okay? Now, we have a coil, a 100-turn coil, right? And that coil is 200 meters away from the lightning bolt, okay? We are going to find the EMF produced in that coil because of the lightning bolt. First of all, will there be induced electricity in the coil? The answer is yes, so that means there has to be a change in magnetic flux. What's the magnetic flux before the lightning? 0. What is it during the lightning? Big, right? So we need to figure out, okay? And I'll write them with deltas this time because we're not going to integrate. The time is not instantaneous, it's 10.5 microseconds, right? We need to suss out what this change in magnetic flux is, right? The change in magnetic flux is going to be a change in BA or cosine theta. Okay, is the coil rotating? No. So it's not a change in theta. Is the coil's area changing? No. So what's the only thing that can change? The magnetic field. So this is going to be delta B times A. What's the angle here? It's 0, actually. The area of the coil is probably pointing into or out of the screen. And depending on which way we say lightning strikes, up or down, and we are not going to get into that conversation right now. Okay? It's either the magnetic field's either directed inwards or out. But in any way, right, whether it's in or out, the area is going to be either 0 or 180, which is why absolute value signs around this thing. Don't care about the positive or negative. Okay. So we know that that's what's going to be. Okay, so my EMF is going to be N, which is what? It's 200 or 100, right? Times my area. Did they tell me what the area is? Kinda. They gave me the radius, right? Times my change in magnetic field all over my change in time. Well, how am I going to know what the magnetic field is? We know the magnetic field of a current carrying wire, right? So mu naught times 6.02 times 10 to the 6th all over 2 pi times 200 meters will give me the magnetic field, right? I have a 100 turn coil. I have an area that's pi times 0.8 squared, 80 centimeters, right? I have whatever this field is that I calculate down here minus 0. You can do 0 minus b or b minus 0. We're going to take the absolute value anyway, right? And then what do I put in for the time? 10.5 times 10 to the minus 6. Okay? Make sure you notice that for all of my numbers here, what did I do? I converted everything to meters, seconds, all the standard units, right? And do I have this one? Yep, I do. This turns out to be 116,000 volts of EMF in that coil. Why do we not collect power this way? If we can get that much voltage. Yeah, that's the problem, right? What's the adage? Lightning never strikes in the same place twice. Stupid, it does. Okay. There are about 100 lightning strikes per second on the surface of the Earth. So that seems like a lot of lightning to capture, right? How big is the surface of Earth? Yeah. You try getting a bunch of coils. It's just not feasible. Even though we could capture it this way, it's not feasible. And even if it were feasible, storage is a problem. We would need the lightning striking all the time, which we know in certain places doesn't happen. And most of the Earth is covered in this stuff called water. Anyway. All right. I will see you on Thursday, where we will get into Lenz's law, your favorite of the semester.